Good afternoon. Today we are going to look at, instead of using the distributive property to do really large numbers, we're going to start with this idea of binomial theorem. Now it's put into the combinations and permutations unit because we use the notation NCR a lot in this problems. Now this would be a question that we're going to end up answering here. What is the 15th term of 2x minus y to the 25th? I have no desire to expand 2x minus y times 2x minus y times 2x minus y 25 times. So we're going to look for a pattern with this. This one's not hard. X plus y squared plus 2xy plus y squared. If I go x plus y cubed, we can write this as x plus y squared times x plus y. We already know the answer for x plus y squared. I'm going to use the box method of multiplication and do my distributive property using the box method. So I've got x cubed plus 2x squared y plus y squared x plus x squared y plus 2xy squared plus y cubed. So gathering our like terms, x cubed plus 3x squared y plus 3xy squared plus y cubed. X plus 4 squared, or to the power, or x plus y to the power of 4 can be written as x plus y squared times x plus y squared. So I'm going to do exactly what I did before. X squared plus 2xy plus y squared times x squared plus 2xy plus y squared. We have x to the fourth plus 2x cubed y plus x squared y squared plus 2x cubed y plus 4x squared y squared plus 2xy cubed plus x squared y squared plus 2xy cubed plus y to the fourth. And the big reason why I like the box method when I'm doing something complicated like this, the diagonals are all my like terms. So I've got x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. Now you should start to see a pattern, particularly when you have the exponents. You notice what the exponents all add up to, in this case, is to the power of 4. So every one of those exponents is going to be to the power of 4. X to the 1 times y cubed. X plus y to the fifth can be written as x plus y cubed times x plus y squared. Our x plus y cubed is up here. Stop with my head. And then we have our x plus y squared, which we've used a couple times already. So we've got x to the fifth plus 3x to the fourth y plus 3x cubed y plus x squared y cubed. And then we have 2x to the fourth y plus 3x x cubed y squared plus, sorry, not 3, that should be a 6, plus 6 x squared y, there needs to be a squared there, I need to have a squared there, and then finally we have plus 2x y fourth. On this line we have x cubed y squared plus 3x squared y cubed plus 3xy fourth plus y to the fifth. Gathering our like terms, x to the fifth plus 5, x to the 4, y plus 10, x cubed y squared plus 10, x squared y cubed plus 5, x y to the fourth plus y to the fifth. Again, the pattern that we dealt with the exponents is the same. Every one of these exponents adds up to 5. There is also, we're going to show a pattern here when we start to look at the exponents. If I write these out, I think I would remember them after all this time, but I don't. X cubed plus 3x squared y plus 3xy squared plus y cubed, x to the fourth plus 4x cubed y to the 1 plus 6x squared y squared plus 4xy to the third plus y to the fourth, and finally we have x to the fifth plus 5x to the fourth y to the 1 plus 10x third y squared plus 10x squared y cubed plus 5x y to the fourth plus y to the fifth. Now, that's kind of ugly looking. If I write these in a triangle, it becomes less ugly. We have 1x plus 1y, 1x squared plus 2xy plus 1y squared, 1x cubed plus 3x squared y plus 3x squared y plus y cubed, 1x to the fourth plus 4x cubed y, 1 plus 6x squared y squared plus 4x y cubed plus y to the fourth. And finally, we have 1x to the fifth plus 5x to the fourth y to the 1 plus 10x to the 3 y squared plus 10x squared y cubed plus 5x to the 1 plus y to the fourth plus 1y to the fifth. That's the patterns that we need to see are across each one of the rows. You notice how the exponents, the x exponent decreases by 1. This needs to be x to the 1 y squared. In each case, the x exponent decreases by 1. The y exponent increases by 1 until we get to the end point, which is the expansion x plus y to the power of 4. There is also another pattern that is very important. And I'm going to just write out the exponents for what we have. Now, if I do, and I'm going to talk about the combination notation in a minute, you notice what's happening here. We have the ones going down the sides of the triangle and across the row. So this here, this set of ones is called a column. So everything like this, that's a column in Pascal's triangle. Okay, so this position here, this 2 is row 3, column 2. Okay. This one down here is row 6, column 4. 1, 2, 3, 4. Don't often use that notation to describe it, but that's how we would describe it if we wanted to. Now, the more important thing about this pattern is 1 plus 1 is 2. 1 plus 2 is 3. 3 plus 3 is 6. 4 plus 6 is 10. 1 plus 4 is 5. 6 plus 4 is 10. The number underneath in Pascal's triangle is the sum of the two numbers directly above it. So the next row in Pascal's triangle, which is the 7th row, because this is the 1st, 2nd, 3rd, 4th, 5th, 6th, the 7th row, which is going to be the expansion of x plus y to the power of 6, the coefficients would be 1 plus 5, we'll have the 1 outside, the 1 plus 5 is your 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6, and 1. Okay? So that is the 7th row of Pascal's triangle. The 8th row, same pattern, 1, 7, 21, 35, 35, 21, 7, 1. So, and I could do the 9th, the 10th, the 11th, and whatever. I just have to keep writing this throughout Pascal's triangle. Correspondingly, each of these numbers can be written in combination notation. So how many ways can we group 0 objects from 0? 1. How many ways can I group 0 objects from 1? 1. 1 object from 1. Same thing. The next row would be 2. Choose 0, 2, choose 1, 2, choose 2. Notice again, we are in the 3rd row and the 3rd column. These numbers are 1 less than the 3rd row, 3rd column, because this is our 1st row here, and that is our 1st column. Then we have 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. If you were to calculate that entire row, that's 1, 3, 3, 1. The 4th row would be 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, and 4, choose 4. 5th would be 5, choose 0, and so forth. It's one of the nice things about Pascal's triangle. It leads directly into combinations. Each one of the coefficients here in this form of Pascal's triangle has a corresponding over here, corresponding combination notation. So the 6th row would be 6, choose 0, 6, choose 1, and so forth all the way to 6, choose 6. Okay. So basically what we have here is this pattern. I can continue this pattern on to the 20th row in either one of these. If I'm going to do the 20th row of Pascal's triangle, I'm going to do it in combination notation because I can pick up some patterns. Here we have our 6th row. it starts with 5, choose 0. Our 20th row is going to start with 19, choose 0, and go all the way to 19, choose 9. Now, if we take a look at Pascal's triangle and add all of these numbers up, and we talk about go up to the 7th row of Pascal's triangle. This is 1, this is 2, this is 4, that's 8, that's 16, that's 32. This guy down here would be 64, and that guy would be 128. Now, if you want to add them up, and don't take my word for it, that's fine, I don't mind. Can you see the pattern that we have? So we're at the 8th row of Pascal's triangle, and we're 128. The 9th row would have a sum of 256. The pattern that we see in our sums is we're doubling. Okay? Now, I'm just going to erase this here because I want a little bit of room. Instead of writing what I did there, I can write it as 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and so forth. Down here I have 2 to the 6, and finally 2 to the 7. Notice how the row number corresponds to what's up here. The first row is 2 to the 0, so 1 less than the row number. Now, if we talk about expansion, this first row corresponds to x plus y to the 0. So that 0 in our expansion is here, but it is also 1 less than the row number. So the pattern, the inscription that we would use, or the equation to describe the pattern would be 2 to the power of n, or 2 to the power of r minus 1. N, the power of the expansion. Where r is the row number. So the row of Pascal's triangle is always going to be 1 more than the expansion that we dealt with. Okay? And that's... So this is the type of question that we're going to have. Determine the sum of the coefficients in the expansion m plus n to the power of 12. Well, m plus n to the power of 12, our exponent in this expansion is 12. So 2 to the 12th. The expansion of m plus n to the 12th will occur in the 13th row. Again, because our Pascal's triangle starts as x plus y to the 0, that's our 1 here, we're always going to be 1 row further along than the expansion here. So x plus y to the 0 is the first row, x plus y to the 1 is the second row, x plus y to the 2 is the third row, and so forth. So here, 2 to the 12th, I don't really care what that number is again. I'm sure we can all do it. Now, when we look here, if we go back to, which I erased for Pascal's triangle, this is the 7th row. 6, choose 0, 6, choose 1, and so forth. This is the 7th row of Pascal's triangle. This one tells me when I'm starting with a 15, this is going to be the 16th row of the triangle if I was to write it out. And this would be the coefficients for x plus y to the power of 15, 1 less than the row number. Well, we have 15 choose 0 all the way up to 15 choose 14. We're missing 15, choose 15. That, if I put the 15, choose 15 in there, we have the entire 16th row of Pascal's triangle. The sum of Pascal's, the 16th row of Pascal's triangle would be 2 to the power of 15. Because we're missing the last term, 15, choose 15, how many ways to choose 15 objects from 15? 1. Okay? So this would be the sum of all of those, but I don't really want to reach for a calculator for it. Here we have, again, this is going to be the 7th row. Starts with a 6. The row number is always one more than that, and the row number is always one more than the expansion. So in this case, this would be x plus y to the 6. So this number here, the 6, is what we're expanding the binomial to. Here we're missing 6, choose 0. So we don't have a 6, choose 0, and we don't have a 6, choose 6 written. So this is the 7th row of Pascal's triangle, which would have a sum of 2 to the 6, but we're missing 6, choose 0, and 6, choose 6, which those are 1 each, so we subtract 2 from them. The other pattern that we want to look at is each row has number of terms that are one more than the expansion. So power of 0, 1 term. Power of 1, 2 terms. Power of 3, 3 terms. Sorry, power of 2, 3 terms. Power of 4, power of 3, 4 terms. Power of 5, 6, power of 4, 5 terms. Power of 6, again, power of 5, 6 terms. Power of 6, 7 terms, and so forth. There's always one more term than the expansion here. Now you also notice that the number of terms in each row is the same as the row number. Again, that's that pattern that we talked about. Right? The row number is always one more than the expansion. Now we can also use this for roots. Now we know how to do this nice simple one using with arrangements with repetition. We know that each one has to move to the right 3 times and down twice. Doesn't matter which path I take, I'm moving right 3 times and down 2. So patterns with repetition, arrangements with repetition, 5 factorial over 3 factorial, 2 factorial. Okay. If we talk about patterning here, there's one way to get from there to there. It's one way to get from there to there. However, there are 2 ways to get to that point. Through this one and through that one. There's only one way to get to this point, and only one way to get to that point, down that way. However, this point could go 1, 2, or 3 ways to get to here. This guy, same reasoning. 1, 2, 3. One way to get to here. Well, we can start to see that same pattern. It's very small, but 1 plus 2. There's 2 ways to get to here, plus 1 way to get to there. So there are 3 ways to get to there. There are 3 ways to get to this point, 3 ways to get to this point. So I can come through here, or I can come through here. There are 6 ways to get to that point. Same thing here, that's pattern, 1 way here, 3 ways there, 4. There's 10 ways to get to that point If you think about a Plinko ball, just letting it go, there's 10 ways that it can get to that point, which is the answer that we did up here. So you can see that the pattern that we developed with Pascal's triangle does apply in this situation also. I'm going to do this one with permutations with or arrangements with repetitions first, and then I'm going to do it with Pascal's triangle. We go right, 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 down, 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 down. We have to get to point C. So we have two steps. We got to go right 3 times and down 4 times in some order to get to point C. We also have to go right twice here and down twice to get the point, to get to the concert hall. So what we have here is we've got 7 factorial over 3 factorial, 4 factorial times 4 factorial over 2 factorial, 2 factorial. Okay. You can use this process with this situation because it enters through 1 point. Okay. Now, the patterning for this one, well, if we just write out 1, because we always have to move closer to where we're going. So we have 1 way along the edges. There's 2 ways to get to this point. 1 through here, 1 through there. There are 3 to get to here, 4 to get to here, 5 to here, 3, 6, 10, 15. So again, we are using Pascal's triangle, the patterning that we developed in Pascal's triangle, and adding these guys up to get to that number there. And the same thing here, 4, 10, 20, 35, which that number there is 35. Now, what do we do to go from here to here? Well, we can separate, if we just treat that guy differently, we'll leave that 35 up there. If I start here, 1, 1, 1, 1, 1. Okay? So there are 6 ways to get from that point to that point, which again works out to be what we have up here, 6. But there are 35 ways to get to that point. But there's only 1 way to get from that point to that point. So it's going to be 35. I got 35 ways to go from here times the 1 to go to there. So I'm just going to slide the 35 over twice. And I'm going to slide the 35 down. Because we're multiplying 35 by 1 that I had earlier. So we have 70. We have 105. We have 105. We have 210. Now you could have got that by going 35 times 6, which is what we did up there. This one you have 2 ways to do it. You can do it with permutations, arrangements with repetitions, or patterning. This guy here, we can't use this formula because I'm missing things. I can't go right, 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 because there's no place to go right here. I have to go down. So this guy does not exist. So, and he would exist if we did it with arrangements with repetitions. There are 2 other pieces missing here. When you have missing pieces, you have to do it with patterning. And we're going to do the same thing that we did up here. We're going to go 1, 1, 1, 1, 1 down here. So 2, 3, 4, 5, 3, 6, 10, 15, 4, 10, 20, 35. Now, what happens when I get to this point here? There are 15 ways to get to here. How many ways are there to get to this point? 15. Because there's only one possible pathway to get to this point down here. And that's through the guy that has 15. The same thing at this point here. There is only one possible pathway that you can get from the 4, where I've written the 4 out. It's through the guy that has 4. So I'm just going to slide the 4 over, and now I'm going to continue my pattern. 10 plus 4 is 14. 20 plus 14 is 34. This is 69. 15 plus 35 is 50. And we have 119 pathways to get there. So anytime you're missing pieces, you have to do patterning in this case. There's this construction over here, and there's a big lake down here, something like that. Doesn't really matter. There's pieces missing from this. Arrangements with repetitions don't work unless you really, really want to do a lot more work than I do. Okay? Now, we're going to use Pascal's triangle to expand the binomial using the 4th row. Now, the 4th row of Pascal's triangle, if you don't remember it, let's create it. I know it's the 4th row because this guy starts at x plus y to the power of 0. We have some value minus 1 to the power of 3. Our x in this case is 2x and our y is negative 1. So my coefficients will be 1, 3, 3, 1. I'm going to be raising 2x to the power of 3. Because again, when we went back to our patterning here, way over here, this is our 3rd row, right? Instead of x, we have 2x. And instead of y, we have negative 1. So I'm just going to replace the 2x instead of the x that we had and the negative 1 in place of the y. So we have negative 1 to the 0. So that's my first term. My second term will have the 2x to the power of 2. So I'm going to take 1 off of that exponent. And I'm going to add 1 to the next guy. And I'm going to continue that pattern. 2x to the power of 1, negative 1 to the 0. And over here we have 2x to the power of 0 and negative 1 cubed. Now we have to tidy this up. Remember that when we have 2x to the power of 3, we are going 2 to the 3, x to the 3. We're not just applying the cube to the x, we're applying it to the coefficient also. So what we end up here is we have 8x cubed. Over here, we are going to have negative 1 times 2 to the power of 2 times 3. So we're going to have a negative 12x squared. Because we're going 3 times 2 squared times your negative 1. And on this one over here, this is supposed to be squared. Negative 1 squared is positive 1. So we're just going to have 6x, 3 times 2, x to the 1. And over here, we have 2x to the 0 is 0. Or sorry, you should say is 1, not 0, 1. So 1 times 1 times negative 1. There's our expansion. It doesn't take me very long, and it shouldn't take you very long to do that expansion in this method. But it's a little clumsier. We did this guy in 2, maybe 3 lines. Okay? Maybe 2, maybe 3 lines. Using our 4th row of Pascal's triangle, which we wrote up here, took us a little bit. Now, here, we could do the same thing with Pascal's triangle in terms of the combination form of it. The 5th row of Pascal's triangle is given here. We know we're going to be using the fifth row of Pascal's triangle because our expansion is to the power of 4. So our first term will be 4 choose 0, x to the 4, 3 to the 0. Because we're going to start our first term, we'll have this guy here raised to the complete power there, and this guy to the 0. Then I'm going to go 4 choose 1, x cubed, 3 to the 1. 4 choose 2, x squared, 3 squared. 4 choose 3, x to the 1, 3 cubed, plus 4 choose 4, 3 to the 0, x to the 0, 3 to the power of 4. Now, again, I'm using my understanding of Pascal's triangle. 4 choose 0 is 1. 3 to the 0 is 1, so my first term is just going to be x to the 4th, which makes sense because there's no number in front of that term. 4 choose 1 is 4 times 3, so we have 12x cubed. 4 choose 2 is 6 times 9, 54x squared. 4 choose 3 is 4 times 27, which is 108x, and then 3 to the power of 4. Because this is 0, or this is 1, that's 1, so we have plus 81. Again, much, much more compact than what I did on the front page here. Okay, and I really, anything bigger than x to the power, or x plus y to the power of 5, I really don't want to do. And here, we don't want the fourth term using Pascal's triangle. I really don't want to do this expansion even using Pascal's triangle. So I'm going to do a little bit of thought process. Our exponent is 12. So our first term of that guy would be 12 choose 0. Okay? Our second would be 12 choose 1. Our third would be 12 choose 2. And our fourth would be 12 choose 3. Okay, I don't care about the rest of those guys. Right? So this is the term that I want. So there's the coefficient. Now let's find the part of the coefficient. Find the rest. Well, our first term will have x to the power of 12, negative 2 to the 0. Our second term will be x to the power of 11, negative 2 to the 1. I'm just subtracting 1 from the exponent as I go from left to right of the x here and adding 1 to the negative 2. This would be x to the 10, negative 2 squared, and this would be x to the 9, negative 2 cubed. I don't care about those anymore. They've got me to where I need to be. I don't know what 12 choose 3 is. I'm just going to grab a calculator. There it is. So 12 choose 3 is 220. Negative 2 cubed is going to be negative 8, and the x to the 9. So multiply 220 by negative 8. Our fourth term in this particular expansion is negative 760x to the power of 9. You would never ever see me expanding x plus y or x minus 2 to the power of 12 using any other method than Pascal's triangle. I will see you tomorrow in class.